So when acids and bases react to form a salt, that salt is not necessarily neutral all the time. That only is true if you have a strong acid reacting with a strong base. In some strong weak combinations, you either have a salt which is acidic or basic, and for some rare cases also neutral. Okay. Now, in this slide, you have some list of air coat rules to determine whether a salt is neutral, acidic, or basic. Now, keep in mind, just a warning, that these are rules which are not, I'll say, scientific air quote in nature, okay? But this is just a rule of thumb, basically to help guide you what the nature of a salt is. We're going to discuss the exact science behind this though in the next slide. And this rule of thumb is actually building up on that science. So in this rule of thumb, you actually look at the anion. The anion of the salt should come from the acid as a result of the neutralization reaction, and the cation should come from the base. Now from there, these anions and cations are just simply conjugate acids and bases of either strong acids or of either rather acids or bases, and then from there you decide what the conjugate acid or base is, what its strength is, and then from there you define whether a salt is acidic, basic, or neutral as follows. Okay, let's say for example, if you have calcium iodide. Calcium iodide is derived from calcium iodide is an ionic compound which is composed of calcium 2 plus and iodine ions. Okay, or iodide ions. So calcium 2 plus is the conjugate acid of calcium hydroxide, okay, which is a strong base. So calcium hydroxide comes from a strong base. And iodide minus or iodide ion comes from hydroiodic acid, which is a strong acid. And iodide is a very, very weak base. In fact, it doesn't even have any basic properties. So for this one, therefore, the product of a strong acid and a strong base should be a neutral salt. Okay, so strong plus strong is equal to neutral. Okay, now if you have a strong acid plus a weak base, according to this rule, you should produce an acidic salt. So let's say, for example, this salt, which is methylammonium perchlorate. Okay, so this actually is from perchloric acid and methylamine. Now, in case you're not here shown these two reactants, we can still determine whether this salt is acidic, basic, or neutral. So looking at the structure, so the cation should just be CH3NH3 plus, and then the anion should be ClO4 minus. Remember that ClO4 is a very weak base of the strong acid perchloric acid, and then CH3NH3, the methylammonium ion, is just one proton more of methylamine. So from here, this is the conjugate acid of a weak base. This is the conjugate base of a really strong acid. So this should make an acidic salt. Okay. And then lastly, or well, at least for these three examples, you have a weak acid plus a strong base which forms a basic salt. So let's say again for this example, you have barium ascorbate, or sorry, barium formate rather. This is formic acid. So the structure here, or barium formate, is actually from barium ions, okay, and the formate ion HCCO minus, okay. One source of barium, since it comes from the base, should be barium hydroxide. Barium hydroxide is a group 2 hydroxide, so therefore it is a strong base. And formate ions is basically or formate ions are basically the conjugate base of formic acid, which is also a weak acid. Okay, so here the barium ions, since they come from barium hydroxide, barium ions do not have any acidic properties at all. So therefore, what dominates here is the formate ion. So this one should be basic. Okay, and then if you have a weak acid plus weak base salt, let's say for example, and we're gonna go over this in class. Let's say for example, you have NH4CN, ammonium cyanide. Then you have to use these rules. If the Kb of the cation, so this should be Kb of the cation, is bigger than the Ka of the anion, then the salt is basic. If it is less than Ka, then it should be acidic. And if they're roughly equal to each other, again, this is a rare case, but nonetheless, it's out there, then you have a neutral salt. Okay, now for the science behind it, I think I actually pretty much explained it a little bit. So let's say, for example, again, if you have a neutral salt, so KCl, for example. So note that KCl was our products from hydrochloric acid plus KOH. Okay, now HCl is a strong acid. Okay, it's a strong acid, and its conjugate base is Cl minus. Okay, remember that from this table, let me see if I can find it. Remember that from this table, we actually said that if you have a strong acid such as HCl, the value of Kb is actually very small. Okay, in fact, it is very small that Kb doesn't even have basic properties. And this makes sense because if hydrochloric acid, okay, was to breaks up completely into H plus and Br minus, or sorry, Cl minus, then if we say that Cl minus or chloride ions have basic properties, then it is willing to right away accept this proton, which basically is giving back HCl. And that's not the case because that's not how strong acids behave, remember. Okay, so for that, we can actually say that, oops, wrong slide again, sorry. For that, we can actually say that conjugate acids or bases of strong acids and strong bases really don't have any acidic or basic properties at all. Okay, so again, here chloride has no basic properties. Potassium from potassium hydroxide also has, which is the conjugate acid, also has no basic properties. Okay, now on the other hand, if you have, let's say for example, sodium acetate, okay, which is this example, or let's actually pick a more simpler one to basically write the formula, sodium fluoride. So if you have sodium fluoride, so this one comes from the reaction of sodium hydroxide and hydrofluoric acid. Okay, now again, sodium hydroxide, since it is a strong base, its conjugate acid, sodium plus, will have no acidic properties. Okay, so this one has no acidic, or well, for that matter, basic properties. Okay, now on the other hand, hydrofluoric acid is a weak acid. Okay, and its conjugate base, okay, which is the fluoride ion, okay, I mean, sure, it's also still a weak conjugate base, but I can tell you that the fluoride ions there can actually abstract a proton. And I mean, it's partly the reason too why hydrofluoric acid, okay, just barely dissociates into H plus and fluorine minus, because fluorine, being an electronegative element, actually wants to abstract that proton, okay, or wants to abstract H plus. Okay, that's why again hydrofluoric acid is a weak acid and it's not considered a strong acid. So fluoride basically has basic properties, and that's what makes this salt. That's why salts from a strong base and a weak acid are always basic. Okay, same arguments apply if you have salts from a strong acid and a weak base. Let's say for example ammonium chloride. Okay, so ammonium chloride comes from hydrochloric acid and ammonia. Okay, the conjugate base of hydrochloric acid is Cl minus, and for ammonia, the conjugate acid is the ammonium ion. Okay, so again, chloride has no basic or acidic properties, but ammonium is a weak acid. So therefore, this salt should be an acid. All right.